All right, so I'm going to go through a few examples here. We're going to use this same 277 480 volt alternator with a internal impedance of 1.6 ohms and a resistance of 0.19 ohms across your windings. We're going to use the same alternator and show what the generated voltage has to be in that when we feed a lagging load, a leading load, and then what to do when we're given this alternator and our load is delta connected. So first two examples are going to be Y connected loads. The third one will be a delta connected load. Okay, so they give us our I line of 60 amps, and we're going to put that on the as our reference point, right? Because the current's going to be the same through all of these components. The same current that's going through the load has to go through the windings, which means it has to go through their XL as well as their resistance. Okay, so we put that one on our reference point. Now, first thing we need to do, we have our impedance of our alternator and we have our resistance. So we're going to have to determine what's going on internally, or how that impedance is broken down within the alternator. So if we have 1.6 ohms of impedance and we have 0.19 ohm of resistance, that gives us we can use Pythagorean theorem. This is way out of scale, and it'll show us that XL equals 1.589. This is R and this is Z. The other thing we can do, the other way to tackle this, if we know we have our impedance, well, we're going to have to do this either way. If we know our impedance and we know our resistance, we can say that Z value of 1.6 ohms happens at 83.18 degrees, right? We take our ratio of our resistance compared to our impedance. We get a value of 0.11875. We take the second function cosine of that, and that tells us that this value is 83.18 degrees, right? So our power factor equals 0.11875. Power angle is 83.18 degrees. Okay? So, we've got 60 amps of current, power factor of 0.9 lagging, so that we determine our power angle, and our power angle of 0.9 is 25.84 degrees. So we know our phase voltage is 277 volts, and based on our 0.9 power factor, we know that this is happening at 25.84 degrees. Okay, our impedance, our volt drop due to our impedance, we're going to take our 60 amps of current multiplied by our 1.6 ohms of impedance, gives us 96 volts, and it's going to happen at 83.18 degrees. Not quite 90, but close, right? So those are our two voltage drops, right? We're losing 200. We got 277 volt drop across the load. We're also going to have a 96 volt drop inside the windings. This is probably pretty unlikely, theoretical values only, but it'll prove the point. So in order for us to satisfy these two requirements, we need to generate enough voltage to supply both of those. So we can take our 277 at 25.84 plus 96 at, whoops, sorry, I hit the wrong button. 96 volts at 83.18, and that gives us a generated voltage of 338.59 volts generated. And then we hit second function exponent, and that is happening at 39.64 degrees.